Okay, so now we're going to look at some examples of problems, excuse me, where you're given data to determine the percentage or actually the empirical formula for a compound. So here's the first example. It says that the analysis of a salt shows that it contains 56.58% potassium, 8.68% carbon, and 34.73% oxygen. And based on this information, you're supposed to determine the empirical formula for this substance. Now, the way I would go about this, and I alluded to it before in the previous video, is that we can assume that we're working with a certain amount of this substance. And a nice round number to assume is 100 grams. And we assume that because if we assume 100 grams of the substance that we have to work with, then these percentages represent the masses of each of these elements present in 100 grams. So in other words, we can assume that we have 56.58 grams of potassium, 8.68 grams of carbon, and 34.73 grams of oxygen. So I like to do this in a tabular form. So the way I like to do this is I start with a table where at the top of the table I have the start of three columns. So one column will have potassium, next column would have carbon, and the next column will have oxygen. All right. So as I said before, we're assuming that the percentages would be equal to the masses of each of these elements. So therefore, I'm going to write the masses of each of these right underneath these symbols. So I'm going to have the mass here. So for potassium, that is 56.68 grams. For carbon, that is 8.68 grams. And for oxygen, that is 34.73 grams. All right. And then the next step, if you remember the process I outlined in the previous video, is to determine the moles of each. So we have to go to the periodic table and look up the molar mass of each element, starting with potassium, 56.68 grams. And we multiply that by 1 mole over the numerical value for the molar mass, which for potassium, when I consult the periodic table, it is equal to 39.10 grams. And I do the same thing for the others. So in the case of carbon, 8.68 grams, multiply that by 1 mole over 12.01 grams. And finally, in the case of oxygen, 34.73 grams multiplied by 1 mole over 16.00 grams. And then I work out each of these. So in the case of potassium, I would divide 56.68 by 39.10, and the result I got there is 1.44, call it 450 moles. And then in the case of carbon, 8.68 divided by 12.01, and the value I got in that case would be 0.723 moles. And then finally, in the case of oxygen, 34.73 divided by 16, and the value I got there is 2.171, so 2.171 moles. All right. And then the next step is that I identify of these three numbers which one is the lowest, and that would be the number of moles of carbon. So what I would do is divide right through by the lowest value, divide through by 0.723 moles, Now if I divide this by itself, I'm going to get 1 here. And if I divide 1.450 mole by 0.723 moles, I'm going to get 1.450 divided by 0.723. Okay, I'm going to get 2.00, and over here I take 2.171 mole divided by 0.723 moles. So 2.171 divided by 0.723, and I get here 3.00. So these numbers, the 3 for the oxygen, the 1 for the carbon, and the 2 for the potassium, will serve as the subscripts in the empirical formula, and therefore the empirical formula for this compound is K2CO3, and that is it. All right. Okay, so that's basically how you would do this example. Now this one is relatively simple, not complicated, because at this stage here we got numbers that are pretty much integers. All right. In some cases you might get a number which is like close to an integer, so you might get something like a 2.98 here. In that instance you'd have to round up to 3. All right. Or if you get a 2.02 here, in that case you round up to 2, round down I should say to 2. All right. So sometimes that's what happens. So that's how we do this one. Now let's see the next one. Now the next one, they gave you the percentage of nitrogen and oxygen in a particular compound, and again you have to find the empirical formula. So let's see how this one works out. So again, I'm going to set up my table. At the top I'm going to put N and O. Again, we're going to assume 100 grams of the substance. So these percentages would represent the mass of each of these. So for nitrogen, that would be 25.94 grams, and for oxygen that would be 74.06 grams. All right. And then, so these are the masses. And then for the moles, it's 25.94 grams multiplied by 1 mole over the molar mass of nitrogen, which is 14.01. And in the case of oxygen, 74.06 grams, we multiply that by 1 mole over 16.00 grams. And we work that out, so 25.94 divided by 14.01, and according to my calculation this works out to be equal to 1.852 moles. And then in the case of oxygen, 74.06 divided by 16, and my calculation tells me that this is equal to 4.629 moles. All right. And again, as in the previous example, when we get to that stage, we divide each of these values by the lower of these two. So in this case, we divide both of them by 1.852 moles. Obviously, this will give you 1. This will give you 4.629 moles divided by 1.852 moles. So let me do that here. 4.629 divided by 1.852. And according to my calculation, this gives round off to 4 sig figs, this gives 2.499. Now this is approximately 2.5, right? So what we'd have to do, because we cannot simply leave this as a fractional number, so what we would do here is multiply right through by a number which converts this to an integer, or better yet 2.499 into an integer, or close to an integer. And obviously that would be the number you multiply right through would be 2. So we multiply this by 2, and when you multiply 2 times 2.499, you're going to get, basically round off to 5.0. In fact, let me do this again just to make sure I'm getting the right thing. 499 times 2. You're going to get 4.998 actually. 4.998, which is close enough to 5. So therefore this is approximately equal to 5. And therefore the empirical formula is N2O5. Alright? So that's how you would do that. Okay, so that's a bit more difficult than the previous one because we have to take it a step further, because when we get the mole ratio here, we cannot leave the answer including the mole ratio in the final equation, because one of them is a fraction. So therefore you have to find some means of converting it into an integer, which means you have to multiply it by an integer to do that. And it turns out that the integer in this case that you multiply by is 2. So we have to take an additional step to end up with the correct subscripts in the final answer. All right. Okay, I think, okay, so the next thing we're going to talk about is how do we calculate the molecular formula from the empirical formula. So far we have determined, or no, we have done 2 examples where we have determined the empirical formula, but sometimes you might be asked to determine from the empirical formula the molecular formula. So the molecular formula can be calculated from the empirical formula if you know what the molar mass is. All right, so if you know what the molar mass is, then you can easily calculate the molecular formula. How do we do that? Well, you have to keep in mind that the molecular formula will be equal to some multiple of the empirical formula. And we typically use the symbol I. In some textbooks, they call it the this I here, the I here. In some textbooks, they call it the integral factor. All right. So basically, what you need to do is to determine the I value, and the way you do that is that you take the molar mass of the compound and you divide it by the empirical formula mass. Now, the empirical formula mass is basically the formula mass of the formula, empirical formula, and you get that by adding all the molar masses of all the elements according to the empirical formula. And I think the next slide gives an example of this. So here you're given the empirical formula, right? CH2. And it gave you the molar mass, which is 126.2 grams per mole. And the question is asking for the molecular formula, right? So to find the empirical formula mass, we simply add up the molar masses of carbon, which is 12.01 grams per mole, and 2 times the molar mass of hydrogen, which is 1.008 grams per mole. And when you add them up, so 2 times 1.008 plus 2.01, you're going to get 14.03 grams per mole, right? So to get I would be equal to the molar mass divided by the empirical formula mass. So that will be 126.2 grams per mole divided by 14.03 grams per mole. And when I do that, 126.2 divided by 14.03, you're going to get an integer, or you should get an integer. Now in this case, I got 8.995, which is very close to an integer, so we can simply round that up to 9. So therefore the molecular formula will be equal to CH2 times 9, which is equal to C9H18. And that would be the molecular formula. All right. Okay, so that's basically it for chapter 8. So the next video will be dealing with chapter 9. Until next time.